Hi, this is Dr. Green, and we are doing a midterm review here. I just wanted to do some computational examples for problems that were either not covered in the homework assignments or just things that I thought would be helpful in preparing for the midterm. So in this first problem, we are looking at the glomerular filtration rate, or GFR, and that's a measure of kidney function. And GFR values are going to be assumed to have a normal distribution. That means we can use the Z table to calculate probabilities. They have a mean of 74.9 and a standard deviation of 27.4. The first question they ask us is, what proportion of the patients have GFR values exceeding 90? So proportions are given by areas underneath the bell-shaped curve, the normal curve, and that proportion statement can be written like this: proportion or probability x is greater than 90. X is your GFR value. So we have to convert this to a question about z-scores to use the table. So here's our z-score formula. We need x, mu, and sigma. So our mean right here is 74.9. Sigma, our standard deviation right here, 27.4. And then the x value we're interested in is 90. So then the z-score for 90 here is going to be the value minus mean over standard deviation. So we're going to take the 90 minus the 74.9. divide by the standard deviation of 27.4, and if you compute that on the calculator, you get 0.55. So what that means is that the z-score corresponding to 90 is 0.55, so this proportion statement is equivalent to saying what is the proportion of z-scores for this distribution that are greater than 0.55. So let's sketch a picture of what we're finding on the bell-shaped curve, normal curve. So on the standard normal curve, z equals 0 is always in the middle. 90 corresponds to a z-score of 0.55, which would be somewhere to the right. And then we want to know proportion of scores above 0.55, greater than. So that's going to be this right area here. Well, the table only gives left areas. So the total area is equal to 1, and then the table will give this left area. We'll subtract from 1, and that'll give us the right area. So in other words, we have to change this to a proportion statement with a less than. So we use the complement rule. 1 minus the proportion of values where z is less than 0.55. Or less than equal 0.55. It doesn't matter. Those probabilities are the same. So that's going to be, this is the less than area. 1 minus will give the greater than area. So let's go to the z table here. So this is the standard normal z table. Back of the book here, standard normal distribution. Notice it gives only less than probabilities. And we want to look up the z-score 0.55. So the 0.5 row, and then we come over to the 0.05 column. 0.7088. So this area is 0.7088. This proportion is 0.7088. So 1 minus 0.7088, and that is 0.2912. Or if you convert to percent, 29.12%. So that's the proportion of GFR values that exceed 90. So next up, we're given that GFR values that are below 60 indicate kidney disease. So now we're interested in below 60. What's the probability a randomly selected patient has kidney disease? So that's saying what's the probability their GFR is below 60. So that's this statement. Probability that x is less than 60. Again, we have to change this to a statement about z-values. Our mean is still the same, 74.9. Standard deviation still 27.4. The x value we're interested in now is 60, and we compute the z-score for that. So value minus mean over standard deviation. So this will be 60 minus the 74.9, and divide by 27.4. And this corresponds to a z-score of negative 0.54. So on the bell-shaped curve, we've got z equals 0 in the middle. Negative 0.54 would be somewhere to the left. And we are interested in x less than 60 is going to correspond to the probability that z is less than the z-score for 60, negative 0.54. So we want a less than probability. That corresponds to the area to the left of negative 0.54, right there. That's a table value. So you can switch back to our table. I've got to get to the negative z-scores. So let's see here, negative 0.5, and then this is the 0, 0, 0, 1, 0, 2, 0, 3, 0, 4 column right there, 2946. So that's negative 0.54. So this area is 0.2946, and areas correspond to probabilities. So this probability, 0.2946. Or if you like percents, 29.46%. And then they also ask us what percentile does this correspond to? Well, 29%, a little bit more than 29%, but 29% of the GFR values are below 60. So this means that that's in the 29th percentile. Notice that we do not round up to 30% because 30% of the values are not below. Only 29%, 29 and a little bit, not quite 30. So don't round up on percentiles. And then in the last part of this question, we are told that a GFR below 15 indicates kidney failure, and we want to know what is the first percentile for kidney function, and is that in the range of kidney failure? So the first percentile means 1% of the data is below that value. So if we sketch a picture of what's going on here, we've got z equals 0 in the middle, and remember 50% of the data is to the left of z equals 0. Well, we only want 1% of the data is to the left. So this little sliver down here is area 0.01, and we want to know what is that value right there. First, we'd find the z-score of that value, and then we'll find the actual value. So the area below that x value is going to be 0.01. That's the first percentile, is what that means. And then from table 1, you want to find the value that's closest to 0.01 in the body of the table. So let's go back to our table here. So these are area values in the table. We want to find 0.01, or the closest thing we can. And if you go here into the table and look for 0.01, 0132, there's 0102, 0099, 0096 right there. That's the closest value. 0099 corresponds to negative 2.33. So that's our z-score. So the table value that's closest to 0.01 is 0.0099. That corresponds to z is negative 2.33. So we know the z-score that corresponds to this is negative 2.33. To find the x value that corresponds, the GFR value, we use the percentile formula. So the x value that corresponds is the mean plus the z-score times standard deviation. So our mean was 74.9 plus our z-score is a negative 2.33 and our standard deviation 27.4. And if you compute this on the calculator to one decimal place, you get 11.1. So that means that on our bell-shaped curve here, the z-score here is negative 2.33. Okay, negative 2.33 and 0. But if we put in x values, then the mean corresponds to 74.9, and the first percentile corresponds to 11.1. And then we're told kidney failure is a GFR of 15. That's a little bit to the right of 11.1, so that'd be about right there. And so the question is, is 11.1 in the range of kidney failure? Well, kidney failure is to the left of 15. So yeah, the first percentile is in that range. So since kidney failure occurs below 15, the first percentile cutoff is in that range of kidney failure. All right, so that should help you out with, I think, more than one question there. In question 2, we're given some data here that summarizes the gender distribution for some diseases: stroke, diabetes, cardiovascular disease, by male and female. So we've got row totals here, column totals here, grand total of 374. And they ask us first a general probability question: what is the proportion of the sample that have cardiovascular disease? So, well, that's going to be, there's 73 that have cardiovascular disease, that's the number, and that's out of 374. And we're assuming it's equally likely that you'd pick any one of those 374. So this is 374 is our total, and out of that total, 73 had cardiovascular disease. So this is CVD out of the total. And to 2 decimal places, that is 0.20. It's actually 0.195, but we'll round to 2 decimal places here. Next up, what is the proportion of diabetics that are female? So it's of diabetics, so it's given that they're a diabetic, and then of those we want to know what proportion are female. So this is going to be proportion of female given diabetics, so the vertical bar there means given. And remember that the given condition restricts your total outcomes. So we're restricted our total outcomes to just diabetics. So people with diabetes were 220. And of those diabetics, the females were 96. So out of that column of 220, we had 96. And then 96 out of 220 to 2 decimal places is 0.44. And then lastly, what is the probability that a male, so we're given that the person is a male, is a stroke victim? Okay, so this is asking what's the probability that they've had a stroke given that they're male. So again, the given condition determines the total outcomes in the denominator. That is male, which there were 200 males. And then out of that 200, how many also had a stroke? So there were 44 strokes from the males from that 200. So 44 out of 200, and as a decimal, that is 0.22. Number 3 here, we're looking at fatty liver disease. The risk of that among alcoholics is 0.32 or 32%. Suppose we have 10 alcoholics. What is the probability that exactly 4 of those 10 people have fatty liver disease? So this is a binomial probability because you either have the disease or you don't. Okay, so it's binomial because it's a yes-no. And so we're going to use the binomial probability formula. So our probability that any one randomly selected alcoholic would have fatty liver disease is 32% or 0.32. So our P is 0.32. And then N, we're going to observe 10 alcoholics. That's our sample size, N. And then we want to know what's the probability exactly 4 of 10 have fatty liver. So that's probability of 4 successes, or you might just write it as probability of 4, or x equals 4. And then remember what you do is you have to do combinations of 4 from 10. So that 4 factorial goes up on top. No, I'm sorry, the 10 factorial goes up on top. And then down on the bottom, we've got the 4 factorial, and then 10 minus 4 is 6 factorial. So these two numbers have to add up to the 10. And then you take your probability of success, which is 0.32, and then the power on that is the 4, and then times 1 minus 0.32, and the power on that piece is the 6, 10 minus 4. And then we enter this into the calculator. So let's see if we I'm pretty sure you can enter this into the MyScript calculator just like I've got it written on the page. So you should find that very helpful. So I entered this in and I got 0.2177 to 4 decimal places, or 21.77%. So approximately a 22% chance that exactly 4 out of 10. So that's binomial probability. And then number 4, let's see, following table shows results for screening tests that's hypothesized to identify people at risk for a rare blood disease. So our results are divided up whether the screen was negative or positive, and then whether or not the disease was present. I've got column totals and row totals here. So first they ask us compute the sensitivity of the test. So remember, sensitivity of the test is the probability that the screen was positive given that the disease was present. Okay, so this is a given condition. Remember, this vertical bar means given. That's a conditional probability. So they have the disease, that's the given. So you look at the disease column, that's 67, that's our denominator. So the given condition determines the denominator. Now, out of those 67, how many had a positive screen? Well, screen positive is this row, that's 52. So 52 out of the 67. And let's see, I got 0.7761. So there's our sensitivity. And then they ask specificity, which is the probability that a random individual would have a negative screen when they were disease-free. So that's a true negative. So you got a true positive, a true negative. And so it's given that they're disease-free. Okay, so no disease. There were 1,208 people total. So 1,208. Again, this is our given condition. Now, out of those 1,208, how many had a negative screen? And that was 1,120. So 1,120 out of 1,208. And if you divide that, get the decimal for that, it's 0.9272. So there is our specificity. And then they also ask us the false positive fraction. So false positive, remember, is the probability that they got a positive screen when they were disease-free. Okay, so the test did not give the correct result. They do not have the disease, but the test said they did. So it's given that they're disease-free. You can't have a false positive unless you don't have the disease. So that's, again, this 1,208. So our denominator is 1,208. And then out of those 1,208, how many had a positive screen? So out of these 1,208, positive screen were 88. So 88 out of 1,208, excuse me. And let's see, if we divide that one, and you will get 0.0728. And then next here, they want us to compute the false negative fraction. So false negative is going to be when the disease is present, but the screen is negative. So it says the disease is not present when it really is. Okay, so it's given that the disease is present, so we have disease, so that's 67 total, so that's our denominator. And then out of those 67, how many had a negative screen? And that was 15. So 15 out of 67, and that is 0.2239. And then in one of the questions they also ask what is the positive predictive value, or the PPV. That's defined to be the probability that the disease is present when you got a positive screen. Okay, so it's given that you have a positive screen, so we're only looking at people that have a positive screen, which is 140, and then out of those, how many had disease present? 52. So 52 out of 140. So 140 is our total. That's the positive screen. Out of that 140, disease was present in 52. So 52 out of 140 is 0.3714. And then to finish up, we will ask the negative predictive value here, so NPV, and that's the probability that a person was disease-free given that they had a negative screen. Okay, so we're only considering negative screens, and then out of those, how many were disease-free? So negative screens were 1135, and the ones that were disease-free were 1120. So 1120 out of 1135. And if you divide that one, you will get 0.9868 to 4 decimal places. 9868. There we go. Okay, so hopefully that will help you do all of the questions that maybe I didn't have examples for in the homework, in earlier homework, or that I thought you